In section 4.1 and 4.2, we talked about a type of number called a rational number. If you remember, a rational number is a ratio of two integers. Oftentimes we call these fractions. So we're going to also need to learn how to write proofs that operate with said fractions or rational numbers. That is the goal of section 4.3, are proofs with rational numbers. We already know that the sums, differences, and products of integers are integers. So we know that integers are closed under addition, subtraction, and multiplication. But most quotients of integers are not integers. So yes, some would be. 2 over 1, that's an integer. Anything else over 1, also an integer. But 2 over 3 is an integer divided by an integer, which is not an integer. That's our rational number. So that's where we're going to begin here, is we're going to begin with our rational numbers. So we talked about this briefly before, like I mentioned, but let's look at our official definition of what a rational number is. A real number, R, is rational if and only if it can be expressed as a quotient of two integers with a non-zero denominator. The non-zero denominator is vital because if we try to divide by 0, we now have an undefined value, and it's no longer something that we can work with in terms of rational numbers. So our official definition here says R is rational if and only if there exists some a and b in the set of integers such that R is equal to a divided by b and b does not equal 0. And while we don't have an official definition for what an irrational number is, it's simply a number that is not rational. So some examples of irrational numbers would be the natural number e. Let's see here, what else? Oh, pi. Pi is another good example of an irrational number. Any of your square roots that are not perfect squares, square root of 2, square root of 3, square root of 5, square root of 7.623589. Those are all irrational numbers because those are numbers that we cannot express as a ratio of two integers where the denominator is not 0. So we're going to start with trying to determine whether or not we have rational numbers. In example 4.3.1, we're going to be looking at several different examples. Let's start with the first one. Is 11 divided by 4, or 11/4, a rational number? I hope you said yes, because it is. Yes, it is, because 11 and 4 are integers, and we're not dividing by 0 because 4 is not 0. So notice we have to include that the denominator is not equal to 0. That's going to become vital when we start writing proofs with rational numbers, because you're also going to have to include in the definition that you are not dividing by 0. So when we define a rational number to say be equal to a over b, where a and b are integers, you will also have to remember to say that b is not 0. More on that on the next page. For now, let's continue with these examples. Negative 5 over 16 is negative 5/16. Is that rational? Yeah, absolutely it is. Because negative 5 and 16 are integers, and 16 is not 0, so we're not dividing by 0. I got a little tricky on the next one. Is 0.281 rational? If you think about it for a moment, you think back to when you were first learning about decimals, you learn how to rewrite them as fractions. So we could actually rewrite this one, because we could say 0.281 equals 281 over 1,000, right? Because that is 281 thousandths. And 281 and 1,000 are integers, and 1,000 is not 0. So you're starting to get the hang of this, I have a feeling. Do we think 17 is rational? I'm guessing you just said yes, because 17 can be rewritten as a ratio of 17 over 1. And 17 and 1 are both integers, and 1 is not 0. The next two sort of drive home this idea of dividing by 0 and knowing whether you are dividing by 0 or not. So the next one asks, is 0 rational? If you think about it, dividing by 0 is not the same as equaling 0. If something equals 0, if we think about it in fraction form, that would be 0 over 1. Are 0 and 1 both integers? Yes. Is 1 not 0? Also, yes. So, yes, 0 is rational because 0 can be rewritten as 0 over 1, and 0 and 1 are integers, and 1 is not equal to 0. But then I gave you a nice, clear example of what is not a rational number. If 7 divided by 0. Immediately we say, no, no, no. We're dividing by 0. This is not a rational number. So here we're going to say no, because 7 and 0 are integers, but 0 is in the denominator. And that breaks our rule, that breaks our definition. So we would say then that 7 divided by 0 is not rational. So we'd say, so 7 divided by 0 is not an element of the set of rational numbers. And you might be wondering again why we use Q for rational numbers. A ratio is the same as a quotient. That's why we use Q. Let's try something a little different. I said I have 0.12121212, and 12 is repeating. And I want to know, is there a way I can rewrite this as a fraction? If you plug it into your fancy TI-83 or 84 and hit math, enter, enter, it will convert it to a fraction for you. The question is, but how? Well, let me show you a really cool trick for these. We're going to say, let x equal this 0.121212 repeating. Okay, we'll start there. Then, if we multiply this x by 100, it's going to move one full repeat to the left-hand side of the decimal. And we're going to end up with 12.121212 repeating. Why would I want to do that? Because now, if you look at these two values, I could combine the 12.121212 and the 0.121212 in such a way that I could eliminate the decimals. My students typically will guess, oh, we're going to divide, we're going to multiply, I'm not sure. So here's the cool thing, it's actually even simpler. We're going to use subtraction. Because if I took 100x, which is my 12.121212 repeating, and I subtract from it just that 1x I had in the beginning, the 0.12121212, then I end up with 99 x's, and it's going to equal 12 point all the decimal stuff minus all the decimal stuff. I'm left with just 12. So here now we can solve for x and say then x, so therefore x is 12 over 99, where 12 and 99 are both integers, and 99 isn't 0. So the answer is yes, it is rational. Will this work for all decimals? No. Some decimals just cannot be rewritten as a ratio of two integers. Like I said before, possibly things like square roots and those sorts of things. But if we have a repeated decimal, oftentimes, yes, we can find a way to express it as a ratio of two integers. Let's look at a slightly more complicated version. It's our last example on this page. I have 0.813813,813, and I forgot to remove, there's an extra one that's not meant to be there. There. This should be 0.813813,813,813. So let's try to see if we can figure out how this one can be expressed as a rational number, because I will say, yes, it can. We're going to let x equal our 0.813813,813,813 repeated. And this time, in order to move an entire repetition to the left-hand side of the decimal, we're going to have to multiply by 1,000 because we have a 3-digit repeat. So we'll say then 1,000x is now 813.813,813,813 repeated. So now when we find their difference and I say 1,000x, which is my 813.813,813,813 repeated, and I subtract from it my x, which is 0.813,813,813 repeated, I now have 999 x's equal to, and now again, all of the decimal part falls away, and we're left with the integer 813. So we solve for x, therefore, x is 813 over 999, where 813 and 999 are integers, and 999 doesn't equal 0. We will find that going through this process and writing out these definitions, these applications of the definition, saying that our ratio is of two integers and the denominator doesn't equal 0 is going to help reinforce our proof writing that we're going to move into next. Let's try writing our first direct proof with rational numbers. We want to prove that the sum of any two rational numbers is also a rational number. So our statement, if we want to write out our universal conditional here, we're going to have to say for all, and we're going to choose two letters. I like to stick with M and N because I can remember them. I do the same thing every time. So we're going to say for M and N, and our first inclination is to say in the set of rational numbers. And then we need an if and a then. But it says the sum of any two rational numbers is rational. So the sum is rational is our conclusion. So our hypothesis is if M and N are rational, then M plus N is also rational. So the problem where that comes in is that we now have our conditional statement is repeating what our domain says, which can be a little bit confusing for the reader. So we're going to say, let's change this rational back here in our domain to the wider set of numbers, which would be the real numbers. And when we move into chapter 6, we're going to talk about this a little bit more. But the largest set of numbers that we're going to work with in this class is going to be the set of real numbers. Rational numbers and integers are special types of real numbers. Irrational numbers are also types of real numbers. So we're going to learn a little bit more in chapter 6 about how they are technically subsets, which will be a more interesting conversation. But what happens here is if our statement for our conditional has that in the if part of it, in our hypothesis, if we have variables that are belonging to a set of numbers, be it integers or rationals, or maybe even an irrational number, then our domain should be the larger set. So it should be the widest set that we can look at. So we would start with a set of real numbers, and then we would say if within that set of real numbers, our two numbers are rational, then their sum is also rational. So the only time we have to walk back our domain is if our hypothesis in our conditional statement is also a statement about belonging to a set of numbers. It gets a little easier to understand as we get through it, I think, a few times too. So here, what will we suppose? Well, we don't have to suppose now that m and n are real numbers such that they are also rational. We can just say suppose m and n are rational numbers. We can jump right to that supposition. That's the nice thing in terms of our proof. So remember, when we're trying to define what our hypothesis means, or what it means for our hypothesis to be true, we are going to rely on definitions. So we're going to rely here on the definition of rational. So by the definition of rational, remember from the last page, that means that both m and n are equal to ratios of integers whose denominators are not 0. So we're going to define them both at the same time. We're going to say let m be a over b, and we will let n, and remember we can't reuse the same variable, so we'll say n is c over d. And now that we've introduced 4 new variables, we have to declare what they are. We can't just introduce these new variables and not define them for our reader. Or if you were programming, you can't include brand new variables and not define what type they are, or your program won't run. So we will include 4 sum a, b, c, and d that are all integers, and b and d, neither one equals 0. Because remember, again, by the definition of rational, we can't divide by 0. Right? Then let's move into now showing that if this is true, then q of mn is also true. And that, in this case, that means that the sum of m plus n is also rational. So we'll say by substitution, then we're going to look at m plus n. M is now a over b, plus n is now c over d. So we need to find their common denominator, which would be b times d. So when we put together our two fractions, we would end up with a times d plus b times c all over b times d. So we do have a ratio now. We have one fraction with one numerator and one denominator. The next goal, because we're trying to prove that this is also rational, is to make sure that we can show that AD plus BC is an integer and that BD is also an integer and not equal to 0. We're going to need to add in a property for that, and I'll give that to you as soon as we get there. So let's let P equal the numerator, AD plus BC. You don't want to let your new variable equal just part of the numerator or part of the denominator, because then you're adding even more steps to your proof that you really don't need. You're working harder and not smarter at that point. And we would always like to work on things a little bit smarter, which means we get through it a little bit quicker. That's all that saying means. So let's let P be the entire numerator and Q equal the denominator. Then we know that P and Q are integers because integers are closed under, and here in the numerator we used multiplication and we used addition. We also used multiplication in the denominator, so we just have multiplication and addition here. The next part is where we need a new property to help us define how we know that that product BD, or which is now Q, is 0. So this is something that we're going to have to add in, and it's called the zero product property. And I'll put it at the top here. So the zero, here, I'll put it up here, the zero product property. And I will let you call that the ZPP. You will not have to always write out by the zero product property. You can just say by ZPP. So the zero product property says that for all A and B in the set of real numbers, if A is not 0 and B is not 0, then A times B is also not equal to 0. And if A times B doesn't equal 0, then A doesn't equal 0 and B doesn't equal 0. This is the perfect example of a biconditional statement. It's also an if and only if statement. So what we're saying here is AB is not 0 if and only if A doesn't equal 0 and B doesn't equal 0. The same is true going the opposite direction. A doesn't equal 0 and B doesn't equal 0 if and only if A times B doesn't equal 0. So this is our zero product property. So how are we going to use this in our proof? Well, we have shown already, or at least we've said, we're going to let P be the numerator and Q be the denominator. We have shown that they're both integers because integers are closed under multiplication and addition. But now we need to invoke this ZPP, this zero product property. So we would say by the ZPP, or you can say by the zero product property if you want, by the ZPP, Q does not equal 0. And we know Q doesn't equal 0 because Q is a product of B and D. What do we say up here? We said that B is not 0 and we said D is not 0. So if neither one is 0, oops, I clicked on the wrong one. If neither one is 0, then their product is not 0. So where does that leave us with our proof? We just said now I have a numerator that's P and I have a non-zero denominator that is Q, and they are both integers. So we would say thus, and we'll continue with our simplification here, m plus n is now P over Q for some, right, for some P and Q that are in the set of integers, and we just showed Q doesn't equal 0. Why am I reiterating that? Because this is the literal definition of a rational number. So we can say then, therefore, by the definition of rational, m plus n is rational, and it has been shown. And you can write it out in words. You could say m plus n is rational. I typically tend to use the symbols. So what I'd like for you to do is to try the next example, which is a similar proof. If you haven't realized, what we just proved here is that addition of rational numbers is closed. So we had closure of integers under addition, subtraction, and multiplication. We're going to find this also holds true for rationals because they are quotients of integers. So they inherit the same properties, the same closure. What I'd like for you to do is use example 4.3.2 as a guide to write your proof for example 4.3.3. So pause here, try your hand at writing the statement and getting the proof started. Hit play, come back and see if we agree. Then pause it again, try to finish it out and come back and see if you've got a proof that looks very, very similar or the same as the one that we're going to have here in a moment. I hope you took the chance to try this problem on your own and try this proof. So our statement says, well, let's see. Prove that the product of any two rational numbers is a rational number. So we're proving the closure of rationals under multiplication. So for all m and n in the set of, well, remember, we're going to have to dial it back out to the real numbers because our conditional says if m and n are rationals, then m times n is also rational. So let's see if we know how to prove this. Well, we can suppose our hypothesis is true, which is that m and n are rational numbers. Let's use our definitions to help us out by expanding what m and n are equal to. So by the definition of rational, we know then that m is equal to a over b and n is equal to c over d for some a, b, c, and d that are all integers, and we know that b and d cannot be zero, all still based on the definition of rationals. So let's substitute these definitions in to our conclusion to see if it is also true. So by substitution then, into mn, we plug a over b times c over d. And this is a fairly straightforward operation. We end up with a c over bd. So we will let p equal the numerator, which is ac, and q equal the denominator, which is bd. Then we know that p and q are integers because integers are closed under, I hope you said, multiplication. So that's the only operation we used here. And we would also say by the zero product property, we also know that q is not zero because q is b times d, and we already stated earlier that b and d are both non-zero. Thus, we continue our simplification. mn now equals p divided by q for some p and q in the set of integers, and q does not equal 0. This is the definition of rational, so we would say, therefore, by the definition of rational, we just showed that mn, the product of two rational numbers, is a rational number itself. And it has been shown. We have two more example problems to get through for this section. They may look a little more complicated than the last two, but they're really not that bad. In one of them, we have to square a fraction. In another one, we have to multiply two different fractions by two different whole numbers, two different integers, and subtract them. We have to find their difference. So as long as you feel comfortable multiplying fractions by whole numbers and combining fractions through addition and subtraction, you will feel fine on these problems. If you feel like you need to go back and look at some fraction properties before you work on this section, I'm sure if you ask, I can give you some links to some great online resources. Okay, so let's start with example 4.3.4. Let's prove if a and b are rational numbers, then 2a minus 3b is also a rational number. So once again, we're going to have if a and b are rational. So our domain here is also still going to have to be for all a and b in the set of real numbers. And then if a and b are rational, then 2a minus 3b is also rational. Okay. So let's try to prove this. We get to suppose that a and b are rational. So this still isn't starting any differently than the previous two examples. By the definition of rational, we know that a equals, well, now we can't use a over b because we already have those two variables being declared as part of the problem. So let's see, let's let a equal maybe c over d, and b can equal, let's say, I over j for some c, d, I, and j that are all integers, and we know the two denominators, d and j, don't equal 0. Then let's move into showing then that 2a minus 3b is also rational. We would say by substitution. We have that 2a minus 3b is now 2 times, well, a is c over d, minus 3 times b, which is I over j. So we end up with 2c over d minus 3I over j, which is 2cj minus 3di all over dj. So let's let p equal the numerator, 2cj minus 3di, and q equal the denominator, which is dj. Then we know that p and q are integers because integers are closed under. And let's see what we have here. We have multiplication for sure. Oh, and we have subtraction this time. So under, subtraction, and multiplication. We also know by the ZPP, by the zero product property, we already know that D and J, neither one, are 0. So we know that Q, which is equal to DJ, is not 0. So thus, we have that 2a minus 3b equals P over Q for some P and Q in the set of integers, and Q isn't 0, which is the definition of rational. So therefore, by the definition of rational, we know then that 2a minus 3b is rational, and it has been shown. Our last example is fairly similar to this one, except that I threw a square in there. I did go back to m and n though, so you can use your a over b. So I'd like for you to use example 4.3.4 as a guide to writing your proof for example 4.3.5. So pause the video here and try example 4.3.5 on your own and see if you remember your properties of exponents when you square your m, and then when you combine your 3m minus your 7n. And when you're done, come back. See if we get the same thing. Okay, let's try it. So let's start with our statement. Our statement says, then for all m and n in the set of real numbers, if m and n are rational, so they're in the set of rational numbers, then 3m squared minus 7n is also rational. So we're going to start our proof in the same place. Let's suppose m and n are rational numbers. Then by the definition of rational, we know that m equals a over b and n equals c over d for some a, b, c, and d that are integers. And remember that b and d cannot be 0. We still cannot divide by 0. So now we move into showing that the conclusion is being compelled by these definitions. So by substitution, we have 3m squared minus 7n. And now we need to substitute in what m and n are. So we have 3 times a divided by b, the whole thing squared, minus 7 times c over d. So when we have a square on the outside of a fraction, we distribute the square to both terms. So here we would end up with 3a squared over b squared minus 7c divided by d. So when we put it together with a common denominator, we end up with 3a squared d minus 7b squared c all over b squared d. And we will let p equal the numerator, remember the entire thing. So it's going to be 3a squared d minus 7b squared c. And we're going to let q equal b squared d. And then we know that p and q are both integers because integers are closed under, and now we've used multiplication. So yes, even powers are multiplication. Why? Because it's repeated multiplication. 3a squared d is 3 times a times a times d. So even exponents, I don't mean even in terms of like an even number. I mean also when we have exponents, we will have multiplication. So here we're using the operations of multiplication and subtraction. We don't have any addition this time. So we know that our integers are closed under multiplication and subtraction, and we know by the ZPP that Q doesn't equal 0 because it is B times D, and we already stated that B and D are not 0. So thus, we have that 3m squared minus 7n equals P over Q for some P and Q that are integers, and Q doesn't equal 0, and therefore, that is our definition of rational. So therefore, by the definition of rational, we know then that 3m squared minus 7n is in the set of rational numbers, or it is rational. You can say it that way, and it has been shown. In the next two sections, we're going to be talking about divisibility, which is directly related to rational numbers. We are never going to talk about division itself directly, because if you have noticed, we have both integers and rational numbers are closed under addition, subtraction, and multiplication, but not division. So we're going to have to think about divisibility and division itself really as a completely different way of looking at it than you might think. We're not going to be doing any actual dividing. Instead, we're going to think about it in a way where we just write it out as multiples of what it is we're trying to divide by. You'll see more when we hit section 4.4.